Dear students, this lecture is the continuation of previous lecture. The main focus of this lecture will be singular points. We will try to learn about the singularities encountered in the second order homogeneous linear differential equations, classification of singular points explained by some examples, and in the next lecture we will try to solve some important ordinary differential equations. A differential equation having singularity at 0 will not have a power solution of the form y of x is equal to summation over an x to the power n. So straightforward method fails in this case, but power series method can be generalized to apply near the singular point. Let us start to investigate the second order homogeneous differential equation of the form ax d squared y by dx squared plus bx dy by dx plus cx y is equal to 0, where the second derivative of y with respect to x can be replaced by y double prime, and the first derivative of y with respect to x can be replaced by y prime. So the above equation can be simplified as ax y double prime plus bx y prime plus cx y is equal to 0. This equation can be written as y double prime plus b of x by a of x y prime plus c of x divided by a of x y is equal to 0. This is equation number 1. Where a, b and c are polynomials having no common factor, then singular point in the above equation are simply those points where ax is equal to 0. Let us consider as an example Bessel equation of order n, that is x square y double prime plus xy prime plus x squared minus n squared y is equal to 0. Here the coefficient of y double prime, that is ax, is equal to x squared is equal to 0. So this implies that x will be equal to 0, and this is the only singular point in the Bessel equation of order n. Whereas in the legendary equation of order n, that is 1 minus x squared y double prime minus 2xy plus n into n plus 1 y is equal to 0. Here the coefficient of y double prime, that is ax, should be equal to 0 to find the singular points, that is 1 minus x square will be equal to 0. So this implies that x square should be equal to 1, or x should be equal to plus minus 1. So Legendre equation of order n has two singular points, that is x is equal to plus 1 and minus 1. Now this kind of singularities can be transformed by substitution t is equal to x minus a. So note that in our case of Legendre equation, we can replace t by x minus 1 to transform the singularity plus minus 1 to t is equal to 0. So we will focus on singular point x is equal to 0. So how we can generalize the power series method to apply near x is equal to 0? Let us write equation 1 in the form y double prime p of x y prime plus q of x y is equal to 0, where p of x is equal to b by a and q of x is equal to c by a. Now it can be proved that each of the function p of x and q of x either is analytic or goes to plus minus infinity at x is equal to 0. So let us consider basic equation of order n, that is x square y double prime plus xy prime plus x squared minus n squared y is equal to 0. If we consider this as equation 2, now this basic equation can be written as in the form of equation 2, that is y double prime 1 over x y prime plus 1 minus n squared by x squared y is equal to 0. Now both p of x, that is 1 over x, and q of x, that is equal to 1 minus n squared by x squared, approaches to infinity at x is equal to 0. So what we should do now to apply the series solution method to solve ordinary differential equation near x is equal to 0? This generalization can be made by assuming that p of x approaches to infinity no more rapidly than 1 over x at x is equal to 0, and q of x approaches to infinity, which is the coefficient of y, no more rapidly than 1 over x squared at x is equal to 0. This is a way of saying that p of x and q of x have only weak singularity at x is equal to 0. Let us express equation 2 is in the form y double prime plus P of x by x y prime plus Q of x by x squared y is equal to 0, where P of x is equal to x into capital P of x and Q of x is equal to x squared Q of x. This is equation number 3. The writing this way will help us to decide about the nature of singular point. Type of singular points: regular singular point. If the function P of x and Q of x both are analytic at x is equal to 0, then that singular point will be known as regular singular point, or mathematically this can be claimed as the singular point x is equal to 0 is a regular singular point if P of x and Q of x are both polynomial or polynomial. So let us do an example to understand more about the regular singular point. Let us consider again basic equation of order n, that is x square y double prime plus xy prime plus x squared minus n squared y is equal to 0. We can write this equation as y double prime plus 1 over x y prime plus x squared minus n squared divided by x squared y is equal to 0. If we compare this with equation 2, that is y double prime P of x y prime plus Q of x y is equal to 0, then P of x and Q of x both approaches to infinity at x is equal to 0. So it is a singular point. Now to understand about the nature of singular point, we will compare this equation with equation 3, that is y double prime P of x by x y prime plus Q of x by x squared y is equal to 0. Here P of x is equal to 1 and Q of x is equal to x square minus n square. So both p of x and q of x are polynomial at x is equal to 0. If we plug in x is equal to 0 in p of x, we will get 1. This is polynomial. And if we put 0 over here, we will get minus n square, which is again analytic. So this kind of singularity is regular singularity, and x is equal to 0 is a regular singular point. Let us do another example. Consider a differential equation of the form x square 1 plus x y double prime plus x into 4 minus x squared y prime plus 2 plus 3x y is equal to 0. We can write this expression in standard form, that is in the form of equation 2 y double prime plus x into 4 minus x squared divided by x squared 1 plus x y prime plus 2 plus 3x divided by x squared 1 plus x y is equal to 0. So here p of x, if we compare it with equation 2, we will get p of x is x 4 minus x squared divided by x squared 1 plus x, or this can be written as 4 minus x squared divided by x 1 plus x, and p at x is equal to 0 will approaches to infinity. Similarly, if we look at for q of x, the coefficient of y, that is 2 plus 3x divided by x squared 1 plus x, and again q of 0 will tends to infinity at x is equal to 0. So this shows that both p of 0 and q of 0 become infinite at x is equal to 0. Let us now to determine the nature of singular point, the expression y double prime plus x into 4 minus x squared divided by x squared 1 plus x y prime plus 2 plus 3x divided by x squared 1 plus x y is equal to 0. Now we can see that this x will be cancelled out with this x squared. So as a result we will get y double prime plus 4 minus x squared divided by 1 plus x, and whole of it will be divided by x, and this is y prime plus, similarly here 2 plus 3x divided by 1 plus x, and whole divided by x squared, this x squared into y is equal to 0. This is now in the form of equation 3, that is y double prime plus p of x by x y prime plus q of x by x square y is equal to 0, where p of x now equal to 4 minus x squared divided by 1 plus x, and q of x is equal to 2 plus 3x divided by 1 plus x. Now p of 0, that will be equal to 4, and q of 0, that will be equal to 2. So both are p of 0 and q of 0 are polynomial. So this singular point x is equal to 0 is a regular singular point, and we can solve this kind of equation by using the series solution method. Irregular singular point. The singular point x is equal to 0 is an irregular singular point if p of x and q of x both or any one of them is not analytic at x is equal to 0. Then this x is equal to 0 will be known as irregular singular point. Other way, if p of x or q of x or both of them are not polynomial of x, then again this x is equal to 0 will be irregular singular point. Example, let us consider a second order differential equation, that is 2x cube y double prime plus 1 plus x y prime plus 3x y is equal to 0. We can write this equation in again standard form, y double prime plus 1 plus x divided by 2x cube y prime plus 3x by 2x cube y is equal to 0. Here again p of x is equal to 1 plus x 2x cube, and p at x is equal to 0 tends to infinity, goes to infinity. Similarly for q of x, that is 3 by 2x squared, and again q of 0 approaches to infinity. Both approaches to infinity at x is equal to 0. So x is equal to 0 is a singular point. Now to check for the singularity, we can write the given differential equation is y double prime plus 1 plus x by 2x cube y prime plus 3x by 2x cube y is equal to 0 is y double prime plus 1 plus x divided by 2x squared and whole divided by x into y prime plus 3 by 2 divided by x squared y is equal to 0. So if we compare this with equation 3, we can find that p of x is equal to 1 plus x divided by 2x squared and q of x is equal to 3 by 2. So this implies that p at x is equal to 0. We can write it as p naught, that is tends to infinity. While q at x is equal to 0, that is q naught, remains a polynomial, that is 3 by 2 x to the power 0. At x is equal to 0 has irregular singularity. And this x is equal to 0 is called irregular single point. So we cannot apply series solution method to this equation. So in summary, if p naught, that is equal to p of 0 is equal to limit x tends to 0, p of x is equal to limit x tends to 0 x into capital P of x. We know that this small p of x is equal to x into capital P of x, and q naught is equal to q0, or it can be written as limit x tends to 0 q of x, which can be written as limit x tends to 0, and again this small q of x can be written as we assume previously, x square capital Q of x. So if p naught is equal to 0 is equal to q naught, then x is equal to 0 may be an ordinary point, of the differential equation x square y double prime plus x px y prime plus q of x y is equal to 0. So this is an ordinary point, and this kind of differential equation can be solved by using series solution method. Secondly, if both P naught and Q naught exist and are finite, then x is equal to 0 is a regular singular point, and the solution of such differential equation can be found by using series method or Frobenius method. If either limit fail to exist or infinite, then x is equal to 0 is an irregular singular point, as we have seen in the previous example. The solution of such equation cannot be found by using the series solution method. So in summary of part 1 and part 2 of the series solution method. Number 1, shifting of index has no effect on the series. That is theorem 1. Number 2, uniqueness of power series. We learn that all the coefficients will vanish independently to 0 for all values of n is greater than or equal to 0. Number 3, ratio test for convergence of the series to find the proper solution and to investigate the singular point. If we have regular singular point for a given differential equation, then we can apply the series solution method to solve the given differential equation. So whenever we apply series solution method to solve a second order homogeneous linear differential equation, we will have to encounter shifting of index, uniqueness of power, ratio test, and investigation of singular points.